Hi, and welcome back. So in the past video, we've been talking about ions, and we've been talking about how sodium, if you just have it on its own, so sodium on its own, was kind of, we said it wasn't nice. It was, if it came in contact with water, it caught fire. Chlorine, similarly, if we had chlorine on its own, chlorine also wasn't nice. It was used as it was poisonous. It was very reactive. Chlorine also just essentially was not a nice thing to have around. However, if we brought these two together and they reacted, and essentially if sodium lost an electron and therefore had a positive charge, and if chlorine, choose a different color, if chlorine gained an electron and therefore had a negative charge, that this compound essentially, or we could say that essentially it's not really like they're what. Anyway, I won't get too ahead of myself, but essentially that these ions together are essentially nice to have around, more or less. This is table salt, and you can eat this, and you can't eat sodium by itself because it catches fire when it comes in contact with water, and you can't eat chlorine because it's poisonous. And essentially what I want to talk about in this video is I've been using that word that I've been talking about a lot in these videos, that word wants, a lot. And I just wanted to do another clarification, and I also wanted to give you a couple of examples, and it's mainly centered around chlorine. So if we said, and I remember that if we had that example of the box of markers on top of the desk and if we pushed it off, and you can imagine that if I have a box of, or let's just say some box here, and we'll just say that that's a box of something, and say that I was holding on to it. Let's say my hand looks something like a Simpsons character, or else let's say I had like a metal, I guess this looks more like a metal clamp, and say this metal clamp just let go, so this clamp released its hold on the box and just let go. We can say that this box wants to fall. That's essentially, it's very similar to when we say that chlorine wants to have an electron like argon. It's very similar to saying, this box, when we hold it above the ground, and let's say, our ground is right here, and we let go of the box, this box wants to fall, that there's some amount of stored energy, that there's some amount of potential energy in the box when it's this far off of the ground, and because there's an amount of stored energy, this box wants to get rid of it. It wants to get to a state where it's more like this, because now it's essentially used up all of its potential energy. It's in a stable environment. It doesn't have to. I guess you could say the box is more or less reacting with the environment. That's kind of a stretch to say that, but when we let go, this box essentially has a lot of potential energy, wants to get rid of it, and so it falls. And that's a lot of how we say, it's very similar to how we talk about these atoms wanting to have a noble gas electron configuration. And one of the interesting examples, and I mentioned in the last example, and hopefully you don't mind me, I guess, talking about this, but chlorine, I mentioned in the last video, was used in World War I as a weapon. It was used as essentially a chemical weapon. It is poisonous. And it was used I think it was used primarily, or one. I think England was using chlorine. And one of the interesting things is, salt, sodium chloride, NaCl, and we can say the ions, and I'll clarify this a bit more. But when I say salt, essentially, this is what is in salt water. This is what's in the oceans. It's what's in table salt. And this is also, I guess, really what England was making chlorine gas from. So chlorine gas, and what was poisonous and what was used as a weapon was chlorine, and it's actually two chlorine atoms form one molecule of chlorine, and it's a gas. And if you don't understand this notation, don't worry, we'll definitely talk about it much more in the future. But chlorine, this was the chlorine that was used that was essentially poisonous. This was the weapon. This atom of chlorine, and it's a neutral atom of chlorine. And this was what was used. The interesting thing, though, is we say that, okay, so sodium in this configuration, when we have salt, sodium has a noble gas-like configuration. We found out it's actually a configuration like neon. Chlorine also has a noble gas configuration like argon. So just like we said, chlorine wants to have that configuration, wants to have that argon-like configuration, we can probably similarly say that chlorine doesn't want, that chlorine does not want to be neutral again. It doesn't want to be in this state. It doesn't want to be Cl2 in its gaseous form. It wants to be, I guess, in a chloride ion rather than a chlorine atom. And we'll definitely talk more about this terminology in the future. And therefore, but anyway, the important thing and what I want to get across in this video is that you can imagine that when chlorine is in this state, it's happy, right? Draw a happy face. It's happy. It's got a noble gas-like electron configuration, like argon. And in our example where we said we have a box and our clamp lets go and the box falls, when chlorine has gained that one electron, when we have the chloride ion, we could say that it's kind of like this box after it's dropped. It's this box that's on the floor, right? Because it's lost, I guess, its potential energy. It no longer wants, it's not like we can say that, we can, I guess, somewhat say that this box does not want to be in the air. That's why it's on the ground, I guess. This box does not want to store up a whole bunch of potential energy. If it gets a whole bunch of potential energy, it wants to release that potential energy again. So therefore, it makes sense that if we want to take this salt, if we want to take sodium chloride, and we want to make chlorine gas, we have to put a lot of energy into the chlorine gas, or into this chloride ion, to get it to do what we want, to get it to turn into chlorine gas. And essentially you can think that, it's the same thing as if, this box dropped and then the clamp has to go back down, pick up the box, and then lift it back up again. And I guess I just wanted to give you a bit of an example, because during World War I and England was using chlorine gas, again, it's, it was used as a chemical weapon. It was poisonous. When England was using chlorine gas in World War I, and this number might not sound enormous, but it is a pretty big number. England used 1% of all the power in the country. 1% of all electricity went into producing chlorine gas from salt, basically, from sodium chloride. Essentially what they did, and I don't know a ton about the exact process, but they dissolved salt in water and then put electrodes, so we could say, if this was I'll just draw like a tank maybe, and say that maybe we had a negative electrode here and a positive electrode here. And I don't know exactly how they would have done it, but, and then we had all around these two electrodes, we had essentially salt water. And then they applied electricity to separate out these chloride ions. And then essentially they were just removing that one electron. They were just removing that one electron to turn chlorine back into a neutral atom. And it used this enormous amount of power. It was 1% of all of the electricity for the entire country. So it was this enormous amount of power. So, when we say, when you hear your chemistry professor say that, chlorine wants to have an electron configuration like argon, or sodium wants to have an electron configuration like neon. Whenever you hear that word wants, you should immediately start thinking, well, there's some amount of energy. There's some amount of energy required, or there's some amount of energy released if chlorine does eventually get that configuration like argon. Or if we wanted to go the other way, if chlorine wanted, or if chlorine does not want to be neutral. Chlorine would rather be in this ion form rather than in this neutral gaseous form. And if we want to produce chlorine gas, it takes this enormous amount of power. It takes 1% of all the electricity for the entire country to be able to produce this stuff. And similarly, you can probably imagine that when we produce, so we say that when we take sodium, and sodium's over here, and sodium gives away one electron and chlorine gains one electron, and we say that sodium wants to look more like neon, chlorine wants to look more like argon. The same way that we had to put this enormous amount of power, we had to put this enormous amount of electricity into chlorine when we wanted to produce chlorine gas, when we wanted to separate out these chloride ions and turn them back into neutral atoms. When we said that we wanted to do that, or when we said that it took this enormous amount of power to do that, what do you think is going to happen when we form sodium chloride from these neutral molecules? We know that sodium doesn't want to be neutral. We know that sodium wants to give away an electron. Same thing for chlorine. We know that chlorine does not want to be neutral. Chlorine wants to gain one electron. What do you think is going to happen, essentially? And I've actually got another video of things catching fire to show you what happens. So this is what we're going to see, and I want to give some credit. This is a video on YouTube from Tons of Fun, That's Me. This video is a reaction of, there's chlorine gas in this flask, and you're going to see they're going to get a little tiny piece of sodium. Really, and it's important to see that this is a very small little chunk of sodium. And it's important to realize, tiny little chunk of sodium, just how much energy comes off of this reaction. So anyway, I'm going to play this right now. It starts playing. There it goes.
A small piece of sodium metal is placed in a flask containing chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
So anyway, hopefully you can see, there is this really pretty violent reaction that takes place. And so you can say that maybe there's a lot of energy. There's a lot of energy stored up inside of these neutral atoms, inside of our neutral sodium atom and our neutral chlorine atom, that wants to get released. And when we say it wants to get released, when we this reaction, we get, you could say, and this is going to be, maybe a little bit, I'll definitely talk more about writing chemical equations for what happens, but we could say that sodium plus chlorine is going to yield sodium, the positive ion, chlorine, the negative ion, and we'll just write these together. And I'll definitely talk more about this in the future about writing chemical equations. And this is kind of an improper chemical equation, but essentially what we get is we put in sodium and chlorine, we get out sodium chloride, and we also get an enormous amount of energy. And we could see from that reaction, if you had done that reaction in your house, your heating bill would be lower because that reaction would generate heat. If it generated light energy. You could also say it probably made noise. It generated sound energy. So when we did this reaction, we put in sodium, we put in chlorine, and we got out sodium chloride plus an enormous amount of energy. And essentially what I want you to get across is that when we start using this word, that something wants to happen, when something wants to happen or doesn't want to happen, if we say, okay, well, sodium really wants to react with chlorine so that they both can have noble gas electron configurations, we can sort of assume that that's some energy. It's going to release some energy stored up. And then the same way that we said that chlorine doesn't want to be neutral. Chlorine would rather stay in this sodium chloride form. If we want to get chlorine gas out of sodium chloride, we have to put in this enormous amount of energy. The same way we would if we had this box down on the floor and we got our clamp and we were going to clamp back onto the box and lift it up. So anyway, hopefully you found this at least a little bit useful. I've been using this word wants a lot, and it's in some ways a good word to use, but I do think it requires at least a little bit of clarification. It makes a lot of concepts in chemistry much easier to understand if we clarify this word wants just a little bit. So anyway, thanks so much for watching, and in the next bunch of videos we'll just keep talking about ions. So thanks for watching, and I'll see you soon.